many of you would probably have seen George in other conferences or familiar with his work recently, in particular for physics-informed neural network, which has become a phenomenal topic in engineering computation. Many of you have presented your own work here around ping. So it's really our honor to have George with us. Unfortunately, George, due to health reasons, can't travel for long distance. Therefore, it was decided here to run George's presentation as a Zoom session.
Thank you, Champagne, for inviting me here. I'm sorry I could not make it in person. This is a topic is dear to my heart, but I couldn't do this, make it this time. So anyway, I want to start with this graphic. It's something that we put together about 5 years ago at the National Institute of Health. It was a thesis paper we wrote at the time before the pandemic on how machine learning shakes hands with multiscale modeling and what good can come out of it. So individually, if we look at multiscale modeling, we can understand emergence of function, we can do predictions, we can elucidate mechanisms and so on, in the context of physical and chemical and biological systems. On the other hand, machine learning, and you can see it's color-coded data here is red, a PD is this orange color, orange color, and then there's ODEs here, so LAMP systems and the theory. So in machine learning, we can explore big data space, of course. We can even manage and tackle ill-posed problems even in high dimensions. And we can deal with, we can create surrogate models which can generalize, and this is what I will talk about today. In addition, we can, so the idea is how to exploit this synergy between machine learning and multiscale modeling at sort of a high abstract level, but then we can make it specific for each system in particular that we study. So before I show the integration, basically interfacing neural operators, that's the ultimate goal of my work is to integrate neural operators with standard methods, for example, finite elements and so on at different levels. But I want to take a detour to show you some of the work that we've been doing in the last 20 years on multiscale modeling, and by that I mean something different in the sense that if we look at the time space diagram, we have the continuum equation, the PDEs up here and all these, but I'm talking about PDEs, and then we have the atomistic models down here. Of course, you can go to quantum level in order to get potentials, but let's stay between atomistic and continuum. In most, I guess, 90% of the multiscale work that I have seen, they try to connect them directly. And several authors, Sidney Yip at MIT, for example, and certainly my group, and I used to direct a Department of Energy center on this topic, on mesoscopic models, which will be sandwiched between continuum equations and atomistic equations. So these models would come theoretically, if you start from bottom up, let's say for molecular dynamics, trying to coarse grain, you'll find this type of models. And also going down from, let's say, continuum equations into atomistic models. For example, if you start with SPH models, then smooth particle hydrodynamics, and you try to go into atomistic, you need to input fluctuations. So mesoscopic models, in some sense, are ideal bridges between atomistic models and continuum models, because on one side, they shake hands with atomistic models in the sense that these mesoscopic models, if they are unconstrained, if they unconstrained, becomes atomistic models. And on the other hand, if you constrain more aggressively, they become continuum models. So they shake hands on both sides. So it is a bridge. Now, there's different manifestations of these mesoscopic models. There are no specific equations, but I will show you how one could derive equations. But the one that I work on is dissipative particle dynamics, method, which I'll talk about a little bit because I will use it later. So if we look at this hierarchy of mathematical models, let's say on the left, typically one will start with a Newton in a bottom-up approach called a Newton equation, go to phase space with the Liouville equation, and then typically we jump to Boltzmann equation with all the assumptions about the collisions and so on. Now, what I have inserted here is actually the Morris-Zwanzweg theory, the Morris-Zwanzweg formulation, which is a formalism to take the atomistic models and cross-grain it rigorously. So we will use this Morris-Zwanzweg formulation, and my group has done a lot in the last 20 years on this topic to go to the next level. So how do you implement this on the numerical side? Now this is the branch here. We'll start, let's say, for molecular dynamics, which will correspond to Newton's law. Then we'll derive the equations of dissipative particle dynamics, which will be, as you will see, stochastic Newton's law with modified right-hand sides. And the smooth dissipative particle dynamics, I have it here because it's really an SPH method, which is derived from top down, and people in Europe like Espanyol and Warren, but Espanyol has introduced this topic in pioneering work. So you can see the analogy between the left side, the theory, and the right-hand side. So the mesoscopic models will be these models, and again, we use them as a sandwich, as a bridge between atomistic models and continuum models. So a little bit about the history of DPD. It was actually developed in Europe, in Holland. Hoegeberger and Kelman was two chemical engineers who first introduced it ad hoc, the method, tried to extend Langevin dynamics in some sense. But at the same time, as you could see, there was also a lot of interest in Boltzmann method. Dissipative particle dynamics, the difference is it's a Lagrangian method. It's just like molecular dynamics method, where we group molecules and atoms into bigger particles, which are virtual particles. So I separated the babyhood. Then there was some interest early on in the 90s, and then the golden era in terms of applications and actually theoretical work started in the early 2000s. So for those of you who have not seen DPD method in the classical form, we take particles, as you can see here, let's say molecules. It could be a fluid, it could be a solid, or it could be a polymer, in fact. So let's say we have some polymer molecules, which we group into these virtual particles. Now these virtual particles interact, but going through this cross-grading process, we have to change the pairwise interactions that we introduce. So for example, a Newton's law will look like a Newton's law, but on the right-hand side, you have a system of three types of forces. We'll have the conservative force, which corresponds to some potential, just like in the molecular dynamics method, but the potential would be a soft potential, in fact, a repulsive only potential in most of the cases, in the simplest form. Then we have a new force, the dissipative force and the random force, and qualitatively these forces are due to the fact that we have removed degrees of freedom, but we then have to put the forces in there. So you can see it's gamma will be a friction coefficient, sigma here will be some fluctuations for the random force, and this omega d and omega r are envelopes of interaction. We don't allow the one particle to interact with every other particle, but just in the neighborhood. So that defines a horizon of interaction. And then, of course, to ensure that we get to an equilibrium state, we have to impose the fluctuation dissipation theorem, so that these parameters sigma and gamma here are not arbitrary, and these envelopes are actually related, as you can see. So this was the initial work. It seems a little bit ad hoc, but I will show you how we derived it from bottom up using the Morris-Zwanzweg formulation. So in terms of applications, and this is just my group, we looked at all sorts of soft matter, from polymers to DNA, colloids, surfactants, and droplets in physical and chemical systems. And then in biological systems, we looked at membranes and proteins. And we looked at red blood cells. We still continue the work on red blood cells, and also platelets. Now, let me go back to the theory and the cross-grading. How do you actually coarse grain a very dense system. And this will apply to any system. It doesn't have to be here I show a polymer, but it doesn't have to be a polymer. It could be a fluid or a solid, as I said. So let's start with the molecular dynamics. We want to do a coarse graining and eliminate the irrelevant variables, but we want to leave the signature of those degrees that are eliminated into the mesoscopic system. So we want to go from this system that's shown here schematically to these larger blobs, these larger particles, in the mesoscopic scale. So I want to give you a very, very simple example to see what happens when you eliminate degrees of freedom, because people have been using, everybody is guilty of that, been using dimension reduction, for example, in ROMs, reduced order models, without actually doing it properly and pretending that everything is all right, but it's not actually. So here I have a two degrees of freedom system, two ODs, and I will try to eliminate y. So we solve for y, as you can see here, we plug in the first equation, and then down here, in this equation, what we have is, for dx dt, I have only 1 degree of freedom since I eliminated the other one. But as you can see, there is this term here, which is coming from eliminating the first degree, the second degree of freedom, y. And then there's also this term associated with the initial condition. But the important thing is, everything now is written in x, but there is this important term here, which is a memory term. So dimension reduction, you can see that in this very simple example, leads to memory effect and noise term. So you cannot simply eliminate degrees of freedom. So as I said, this is everybody's guilty of that because we're not doing it right. But you can see right away that when you eliminate degrees of freedom, when you go from a dense system to a coarser system, and as I said, this is also for people who do POD, and routinely they forget about that. They forget about that because they assume incorrectly that there is a scale separation. So if there is a scale separation, in fact, so let me introduce this parameter here, epsilon, in the same system of equations. If there is a scale separation, you can see now we can derive again the equation, and there is a term here, the memory term, that goes from 0 to t, but there's epsilon. So as you can see, when epsilon goes to 0, then this term, this becomes a delta function, and then this whole term becomes epsilon. So if you can see, then you get an equation which is dx dt equals 2x, which of course you can get immediately if you take in this equation epsilon go to 0 and add these equations. So in other words, there is a simplification only in the case where epsilon goes to 0, which means you have a clear separation of scales. Then this term has to be eliminated. So it's simplified. Now let me go back to the theory of the Morris-Zondrich formulation, and you can find the exact derivation of equations here. But basically, we start again with a system of equations like that, and then we define the conditional expectation projection operator. In other words, I take an operator L and I will project it into the degrees of freedom that I want to keep, and then there is also Q will be the operator, the complement that corresponds to the degrees of freedom that we eliminate, and P plus Q is the identity operator. So we can do some manipulations here, but we can relatively easily derive this equation now for it's called the Morris-Zondrich formulation, where we have this term. This term will be what we have also at the small scales, what we will call conservative force, the first term that you saw in the DPD formulation. And then we have this term here, which is a memory term. And then we have this term here. As you can see, the last term depends only on Q, which are the non-resolved, the unresolved degrees of freedom. So we will call that, we'll refer to that as a random term. Now, we have to work a little bit to see what this term is, and then you have to be specific to find new coordinates of the coarse grain system. So in my case, when I take a polymer and I coarse grain it like this, I go from this atomistic system to a coarse grain particle. I define the radius, the big radius of this virtual particle Ri, and then the total momentum of the big particle will be a sum of the momenta, and the mass is the mass, the total mass of the big particle is the mass of the small particles, and so on. And then you define a phase variable A. So I don't want to derive all this, but down here is the equation, and it has three parts. The first part, omega here will be a partition function. Beta is 1 kBt. So the first part is this conservative force, which comes from the atomistic part. The second part is the memory term, which is interesting because it has the velocity, right, of the big particle, pressure over mass, but also it has this correlation here. It's a cross correlation actually of the random force. So the kernel in the memory is really and that comes from the fluctuation dissipation theorem. It automatically satisfies this. So and then the last term, which depends on Q only, the eliminated degrees of freedom, the unresolved degrees of freedom is like that. So you have three parts. We can simplify it further. So you can see, for example, let's say there are no conservative force, and so just the last two terms, the generalized Langevin equation that you may have seen is derived directly from the Morris-Rundvik formulation. It has this term with a kernel K, and then this random force, the stochastic equation. Here I wrote for a single. Okay, so now for how does the DPD come in? The DPD comes in for this pairwise interaction, which is, as I said, comes in from two particles interacting, and you have this form. Perhaps a simpler way to see this is if I have a non-Markovian model, which means that you really keep the memory. You have something like this. This is which I just showed, the generalized Langevin equation, and of course the Markovian model for that is this form, because the K memory kernel becomes a delta kernel the same way I show you in the two equation model that you have a delta function for kernel if there's a clear separation of scale. So these Markovian models with memory, with no memory, automatically imply that you really have a clear separation of scales, and that's what is used often. And then you have this pairwise the DPD interactions for these equations, which so this is in some sense the direct derivation of the equations that I show you for DPD using this powerful theory. But the theory can go beyond DPD, can produce different coarse-grained models. Of course, you have to deal with them. You have to learn how to solve them, and it's not clear at all. So if you didn't follow what I said schematically, this is what we have. We have an atomistic system with a molecular dynamics and a hard potential with lots of particles. And then we coarse-grain, but we coarse-grain rigorously, and we go and we derive this type of potential, which is a soft potential, in this case a repulsive only potential. And again, this is in the simplest form. There is instead of two body interaction, there's also a version of many body interactions where you can include attractive potential for slip conditions and other more complex multi-phase physics and so on. But you see, we have a soft potential from a hard potential, and we also have pure particles. So at the end, the speed up of this coarse-grained system is due to two factors. One is that you have fewer particles by a factor of 10, 100 per 1,000, let's say, depending on the coarse-graining degree. But also you have soft potentials like this, and the time step is much, much larger, orders of magnitude. So working with a coarse-grained model, properly counting both memory and random forces, it requires, of course, to now the earliest, for those of you who are doing larger simulations, it will fall under this category. The problem is we don't use backscattering, which will be the stochastic part in the LAS, because it's very hard to deal with it in the computation. So again, that's another drastic simplification that people have done over the years, but it's not theoretically, it's not correct. Anyway, these are some of my thoughts on cost graining, the way we have approached it, and the equations we derive. So for those of you who are working in this area. Now, as I said, the reason I'm interested in this because I want to develop a bridge, an interface between the Navier-Stokes equation, for example, and molecular dynamics equations for various reasons. I don't need to explain to you why one would need to use one or the other or both at the same time. And typically people put Navier-Stokes and MD together, and then they try all sorts of tricks which will work for one case, but usually doesn't work. So that's in space. In time, what you do in time, you also have different multi-rates at 3 different levels. So one has to choose a time scale, a proper time scale, depending on the phenomenon you study, how often you communicate between those 3 domains. So here I chose, for example, in the triple-decker algorithm, something we published in the Journal of Computational Physics many years ago. But it's a triple-decker because DPD would shake hands both with MD and Navier-Stokes at the same time. And again, DPD, you can prove rigorously. If you don't cost grain, it becomes molecular dynamics. If you cost grain to the limit, it becomes, you recover the hydrodynamic equations. So it's very nice to have this bridge because naturally it tends to those 2 states. And the way we overlap is by developing this in boundary conditions, stochastic boundary conditions, because they require fluctuations to do this. So I don't have time to talk about this, but I wanted to show you that basically there's 3 steps. You start, let's say, from bottom up. You integrate in the molecular dynamics domain during this tau period before you start communicating, and then at the end of tau, you overlap and you take a slice here and you pass it to the DPD domain, and you do the same thing on Navier-Stokes. And as you can see, right in the middle is DPD shaking hands with both domains. So multiscale modeling, it is characterized as shaking hands, as I showed, and in fact the integration with machine learning is kind of similar, at least at the high level. Here are some examples to validate this. We use a wet flow, which has a linear, but you can see here the molecular dynamics part. It overlaps with the DPD and overlaps seamlessly with the Navier-Stokes, and also Poisson flow. These are for channel flows. But I have a cavity flow here. Now one could use, because of the singularities, for example, in the driven cavity, at the corner you can use molecular dynamics, and then you can use a slice of DPD and Navier-Stokes here. And this is kind of a little arbitrary just to demonstrate, but you get pretty continuous forms of the velocity, as you can see, without fluctuations looking at the mean. How do you deal with fluctuations between MD and DPD? It's a very interesting topic. I will not talk about that here, but we have some papers in the literature. But I want to show you something that we did about 10 years ago, more than actually, where we wanted to simulate the entire brain vasculature in 3D, as you can see in this picture here. But then there is this is a real patient circle of Willis. We wanted to look into the thrombosis for big giant aneurysms, which are these dilations. There is this thrombosis, and we wanted to go down to molecular level because we wanted to capture platelets and red blood cells and so on. And the question then becomes, you have this huge simulation of, we did up to 300 arteries in the brain in 3D, and then we also had the DPD simulation, which is very expensive on its own. And we had to use a big supercomputer. You can see some details here from the code Nectar spectral element code that we developed over the years. And I don't know if you can see, but now we have a movie that shows the flow in the circle of Willis. Then we zoom in the dilation in the aneurysm. This was done on 300,000 course at the time. It was a Gordon Bell finalist. And then you zoom in where right at the apex, where we expect the rupture of the aneurysm, and we see the deposition of platelets, for example, taking place, and how this could trigger rupture of the aneurysm. So, I mean, this is the reason I show that is to make 2 points. One, this requires hundreds of thousands of cores to do such a a problem, at the end it's such a big computation that you cannot do and you cannot really learn a lot. So, but it can be done in some sense. That was a proof of concept at the time, and we made it to the Gordon Bell finals. At that time, the Japanese won because they did a very big molecular dynamics simulation, and they killed us. But the other point I want to make is that one can use data, some data, to avoid doing such big computations. So one can use data as closures to make a smaller computation like this instead of this huge computation. So that takes me to the second part on machine learning, and so most of the times what we are trying to simulate is a case where we know all the physics, we pretend we know all the parameters and so on, but that's not the case. Imagine you have a reactive transport, non-Arrhenius chemistry. You don't know the kinetics. You may know the diffusion processes, advection process, but you don't know in reactive transport. In many other cases, even in turbulence, we cannot resolve all scales, or in the problem that I just showed you, we cannot resolve the very small particles compared to even 1/9 of the size of a brain. So in that case, you have to blend seamlessly data and physics. And unfortunately, the data is not pretty as you want it. It's not on the boundary conditions, it's everywhere. It could be scattered, it could be asynchronous, and you have to assimilate all this data. The geophysics techniques and assimilation methods, data assimilation methods, are inadequate. For a long time, we have been using Kalman filtering and so on, which are linear tools. But if you try to use something like a joint, it's so expensive it breaks the bank. So we introduced this PINS, physics-informed neural networks, a long time ago, and the idea is we have some data, and that data will be expressed by this match between where the predictions of the neural network, which is this state variable u, minus, let's say, the data that you're given. But also we know that u satisfies some equations. Here, for example, I have a parameterized Schrödinger equation. So I need these residuals to be 0, and I can compute. So I have a second term. And I can compute all these operators exactly using automatic differentiation. So in PINS, we don't use grids. We remove the tyranny of grids, of mesh generation. As you know, that I call it tyranny because it takes a long time, and we depend on the grid too much. But all these operators can be computed exactly without artifacts like numerical dissipation, numerical dispersion. To compute the residuals, and you can then derive as many data points from the conservation laws as you like by increasing this number NF, and basically doing a Monte Carlo sampling of space-time of your system. You don't necessarily need to know all the terms of the equations. Here I have parameters which are known, because having data and then you blend seamlessly the data term and the physics term, and you just use standard commercial machine learning optimizers and so on to get done. So this is PINS. Now, what's the problem with PINS? Well, there are lots of problems because we're still in infancy of PINS compared to finite elements, which are almost 100 years old now. But going back to Courant, but there are also some progress, and the main problem is for forward problems the cost. How do you eliminate the cost? Because, as you know, any neural network takes a lot of time to train, and PINS is not the exception. Compared to finite elements, are more expensive. But one idea is to go to a higher level of abstraction, and this brings me to neural operators and the DeepONet that we introduced for first time in 2019. And in neural operators, you're not going to solve only for one case and optimize every time. You're going to go offline, solve, let's say, for a plurality of conditions, distributions, so not just one boundary conditions, but all possible boundary conditions that you can imagine your system can encounter. Not one Reynolds number, but all Reynolds number, range of Reynolds numbers. So you learn offline. So the inputs now are not data; they're actually functions, and the outputs are functions. So now, for a standard neural network, which is a function, we have data in and data out. Here we have functions in and functions out.
So what will connect this mapping is really an operator. So we're learning an operator G here, which takes an input U and takes it to an output S of X, as shown here, for example. In other words, we learn this equation. Now this is a system identification. So after you learn, you don't really need to optimize again. So you can actually forecast in real time. So for us, this is ideal because we can think of this as surrogates. And people are using reduced order models. It's very, very similar, but these operators generalize because you can actually learn the operator, generalize much better. So in reduced order models, we have fewer degrees of freedom, but in neural operators, in neural networks in general, you over-parameterize, right? You have more parameters than the data points. And that gives you the ability to generalize, just like our brain. So how we built this neural operator, it was kind of, in some sense, inspired by the human neuron. That's why I have it here. So we have these branches, which are the inputs. So I dedicate different neural networks for different inputs. Here I have just one neural network for a branch. These are called branches or dendrites, branches. And then I have another neural network for where the computation is done in the soma or the trunk. And then those two together, you cross them, you get this part here, which is the synaptic output. So again, this is what we're talking about. From functions, we have a finite dimensional space to a finite dimensional space. For operator, we go from infinite dimensional space to infinite dimensional space. And of course, that's a huge difference introducing neural operators. By the way, the computer scientists are using this now in graphics and other applications. It's used under the name of neural fields. But neural fields is actually neural operators. Computer scientists are not very good in math, so they are a little limited. Just kidding. So when I started, I was interested to see if there's actually theory, just like the universal approximation theorem for functions by Saitego, if there's something like that. And I ran into this theorem of Chen and Chen that I popularized. Nobody knew at the time. I met Professor Chen at the University of Fudan in 87 years young. And he told me that he thanked me that I discovered his paper because nobody even paid attention to it, although it was published at the same time as the universal approximation theorem for functions. So basically the theorem says exactly what we wanted. In other words, if you're trying to determine this operator G that takes U to an output G of U of Y in space Y, that can be approximated arbitrarily by two neural networks, just like I drew them. One with a trunk, you can see here. And this is a single layer. At that time in the 90s, they use only shallow networks. And then another one, which is the branch, which is the input. Now, you take U, the function, which is continuous. You sample it or project it, if you like. But then the neural network will present as a continuous again. Although you start with a continuous function, you project it, these are the xj at sensor points, let's say. And then you reconstruct it with a neural network, so you have a continuous field. And then this basically here, this term here that I have in the big square, this is a coefficient which I will call, let's say, bk. And this here is a basis which we'll call phi k. So phi k of y. So we can expand this g of u of y, the operator in the continuous operator in the output space, which is a function now. G of u of y is a function. Then you can do it as you think of a Fourier series as sum of bk coefficients that are computed based on the inputs times a phi k, this nonlinear basis of neural network. So in our language, in finite elements, this is how we want to write it. And in fact, I show it here. Oops, I lost it. Right. So it's right here, and then this is the basis, and the way we construct the neural network, you may have seen it is, again, this is the branch, this is the input, which is projected from U to some points, and then here's the trunk. The trunk again gives you the basis, phi k, which is this basis right here. Okay, so that's it. I want to show you how we use that operator for multiscale modeling. So I have two examples. First we had to prove that the theorem is actually extend it to deep neural networks, because it turns out that the reason that nobody used the Chen and Chen theorem to construct a single layer is that you run into the Kershov dimensionality in the input space, so it's not computable. But going to deep neural networks, and that's what this theorem here that we had in the paper in Nature Machine Intelligence shows, that you can actually break the Kershov dimensionality in the input space by going to deep neural networks. Okay, so here's my first example. I want to grow bubbles, and bubbles which are small and grow, or really, really tiny nanobubbles. So I will go to, first I will look at sort of bubbles that are described by this famous Rayleigh-Plessé equation. So given a pressure difference between the bubble and the ambient, you can derive from here easily how R grows in time. Now, I'm not going to use this equation. I'm only going to use it to generate data, but actually I will discover this equation as an operator. The DeepONet will discover this equation. But you can see here we have the viscosity, we have surface tension, and so on. So from 1 micron and above, this equation is valid. Bubbles of initial radius of 1 micron and above, this equation is valid, has been validated, and so on. So what we'll be doing is this exercise here of training, where for different pressure distributions, delta P, which will go as a function into the branch, I will produce R as a function of T, okay? So I will do that for the arbitrary different distributions. I can use a Gauss random field to pull this delta P, but I will do it for lots of them, it's hundreds. So after I train it, and here I have some details of how you train it, after I train it, then I take these arbitrary new distributions, and I want to plug into my DeepONet, and I don't do any training anymore. I want to see if I can predict the multi-rate dynamics that comes out. And in fact, these are three different cases, for 3 different distributions coming from up here, from up the corner. You can see that I can get a very accurate, I don't know if you can see the RP, the Rayleigh-Plessé equation is with blue. Again, I didn't use it, I only used data for it. And the DeepONet is really on top of it. And you can see there's a multi-rate dynamics here, and also a slow dynamics right here. So that's why I call fast rate and multi-rate. In all 3 cases, I do pretty well. What is the cost of DeepONet? Well, there's a DeepONet cost to do it offline, the training, but actually real forecasting inference is a microsecond, because you simply interpolate in the functional space. Now, people will say, well, this is just a time, there's no PD, this is an ODE. Why don't we use a recursive neural network, LSTM, or even transformer now to do it? But let's say LSTM. LSTM is a pretty good network, and you can see a comparison here between on the top row of LSTM and DeepONet. The LSTM is doing an excellent job also if you have a lot of points per trajectory. Trajectory means the growth of the R of T. However, as you start coarsening these, and in other words, if you use fewer points, let's say 80 points, you can see that it loses the high frequency compared to DeepONet. And if you go to 20 points per trajectory, you can see that LSTM can predict the long-term dynamics, but the fast rate dynamics can only be computed by DeepONet. So that's why I said generalized better. Although LSTM is a pretty good network, most of the times in this dynamical system didn't do as well. Now, what I told you here, and this is the radius, the initial radius, R0 at T equals 0, is something that happens here. The large bubbles, as I have here, relatively large, from micron up, can be described by the continuum equation and so on. But what happens to tiny bubbles? In tiny bubbles, we have to go to molecular dynamics. In fact, I do stochastic DPD, what I just told you, that's why this introduction, I use DPD to train this network, okay? Now, a DPD simulation, as you know, a molecular dynamic simulation is expensive, more expensive than DPD, but DPD is still expensive because you need to put lots of particles to fill this space. So first we're gonna train now, I'm gonna feed the operator both with the continuum data, which I already did, but also now I will add data in here. So I need to do independent 50 DPD simulations. Every simulation takes about 50 hours. So I built 50 bubbles, but just to show you how this looks, you can see the stochastic fluctuation here on this plot. So in this here, we see that the mean radius that I predict with DPD and DPONet is the same, except DPONet takes again 1 microsecond. After I train, it takes 1 microsecond, but DPD will take another 50 hours for another pressure difference. So now I will feed DPONet with this stochastic data, and I have to do the proper scaling because the only thing I really need to do here, I don't need to handshake. In fact, I will just overlap the continuum domain with the, here's the demarcation line, right here, the boundary. So I'm going to overlap. So I'm going to take the DPD all the way to here, and I take the continuum all the way to here. And that's the only thing I do in terms of creating a multiscale, seamless multiscale operator out of DPONet, the neural operator. I only feed data independently and overlap in that regime. Of course, you have to make sure that the DPD gives you the correct result, and in fact, we have verified that DPD tends into the Rayleigh-Plessé equation right at the interface. And here's a paper in JFM. You can look at the details, but these are some examples. This is right here, shows the overlap where actually the Rayleigh-Plessé and the DPD and the DPONet are all coincide, all the results. Down here, you can see that the Rayleigh-Plessé actually deviates from the DPD, but DPONet agrees with on that side because it's trained with the DPD. It gives you back the DPD or interpolates in between. And here, again, we have a Rayleigh-Plessé and DPONet agree. And there's a bunch of simulations here. It's explained in the paper. So we have a seamless integration between atomistic scales here and using a neural operator, and the neural operator can now just spit out the results at a fraction of a second, as I said, after it is trained. Of course, the training is expensive, but imagine every time for a new radius, initial radius, you do a simulation, you need 50 hours. The Rayleigh-Plessé, of course, is very fast. You don't need to do that, but this is a pedagogical, more like a pedagogical example to make the point. And I want to finish, I have just a few more slides, a couple of more slides, with this, how we take that now, multi-scale modeling with machine learning interfacing, let's say, finite elements with deep neural operators. And here, this is a schematic. So imagine you have a domain, a relatively large domain. Here I look at stresses and solid mechanics, so we have an example also from fluid, but here's an example. So somewhere in the middle here, there's something important happening. For example, you may have a region of plasticity, you may have fracture, you may have something that has to be described by something expensive. It could be a nonlinear finite element, it could be one of these molecular methods which are expensive, it could be peridynamics for those of you who are interested in peridynamics, and fracture, it could be fracture, as I said, and so on. So that's the expensive part. And then outside you have linear finite element. Now, personally, I don't know of any method that time dependent that have solved this problem, the multi-scale problem, where you try to interface, let's say, molecular dynamics and finite elements, and there's something evolving in time. I know of steady states, about 10, 15 years ago, there's a lot of interest in bridging molecular dynamics with solid mechanics, let's say elasticity, which again is the wrong thing. You have to put DPD in the middle. But anyway, that was my point in the first part. But the point is, if you have a time dependent case, and the linear finite element and the finite element outside takes a second to compute, and the inside takes 50 hours to compute, then you cannot really do a simulation. So you need a surrogate. Of course, you can do ROMs, but ROMs, as I said, are limited. They cannot generalize, despite the popular belief, or the propaganda, I should say. But neural operators will generalize, as I just demonstrated. So the idea here is to use a neural operator to take into account train offline. So this, if you like, these neural operators are like ChatGPT. They're foundation models. You train them offline, and then online you can use them in real time. That's what I'm trying to also do here, where I will interface finite elements with neural operator. The neural operator will represent molecular dynamics, or SPH, or nonlinear finite element, the expensive part. just as a proof of concept. And now how you interface, because now you have spatial conditions to satisfy, for example, fluxes and so on, like we do in this continuous collecting. So you can overlap, or you can use, like in the Schwarz alternating method, or you can do non-overlapping, and there's ways to deal with this using what I have developed, was developed by Quarteroni. In this paper, I call it developed the Zanoli patching, which is an intensive relaxation method. So, and what I want to use as boundary conditions is these Robin boundary conditions, where I will take into account both displacement and stresses, if you like, temperatures and gradients of temperature. Same thing for fluids. So Robin boundary conditions, R1 and R2 will be constants, positive constants, which we can optimize in the process, so we have the best seamless integration between the neural operator and the finite element. So as a pedagogical example, let's solve the Poisson equation. So we solve the Poisson equation everywhere, but I want to insert the domain here, where the neural operator will learn independently. Here this offline on the right. Offline will train the neural operator from finite element solutions. So this is finite element, just as I said, to a sanity check. So we train the neural operator with lots of samplings at the boundary conditions. So this is what is shown from the Gauss random field, for example. And then the neural operator can solve for arbitrary boundary conditions, can solve the Poisson equation inside the subdomain, the small domain. And here, this is here to show you that we overlap. Gamma 1 belongs to the finite element outside, gamma 2 is the neural network inside, which is also finite element, and this is exactly what is shown here. So, how we train the neural network in this case is basically we take from the boundary conditions on the gamma 2 interface on the branch, and then X space, and then what the output is, the solution is a neural network. Okay, that's how we train. So after we train it, the coupling becomes seamless, as you can see here. For example, this is now the hollow domain, the outside domain, which is just do finite elements after we converge in this iterative process using a Schwarz method. And this is the small domain inside here. The small domain inside, you can see the errors are minimal. And if you look right at the boundaries where we have the seams of interfacing, there's a total agreement between the neural network and the true finite element solution. Okay, so that's a very simple example. Can we do better? So this is now the inside domain. This is a elastoplasticity case where we have finite element in the yellow domain, and then inside this circle, I will have let's say, a nonlinear finite element, and I get the data from Abacus, for example, from Similia, Abacus, and how we train this. So the neural operator will represent now the nonlinear finite element, the elastoplastic part, which is in this circle. There's an overlapping, as you can see. In terms of boundary conditions, you can see here I send stresses, and then I bring back displacement. So I need to train a neural operator that takes arbitrary displacements on the boundary. This is shown here, that comes from finite element, and then it gives a stress field inside the domain, inside this circle. So again here's the interface of the branch. We get the boundary conditions, and then and different plurality of different conditions, and then we get the stresses. And the error, just to train the neural operator, the error is below machine accuracy and single precision. You can see 10 to the minus 7, 10 to the minus 8 errors for the stresses. And again, if I look at the right where have the seams at the interfaces, I see continuity, and also the fields, the errors are very, very small. You cannot really see between the two domains. So there's a seamless interfacing. And the last example, and I'm done, comes from particle methods. So now here I use SPH. This is a case of hyperelasticity. So I use SPH to solve the hyperelastic material here. Outside the material is linear, and that's where I would use depot net. Okay. Now this material, we just make it a little more interesting. We have fibers reinforced in the vertical direction, so we really have an anisotropic case. And And here, again, we exchange displacement and stresses, as shown here. So I need to train twice. I need to go from displacement to stresses due to displacement to stresses due to S. And then also I go from stresses to displacement. So it's kind of the inverse neural operator, which I train twice. And this is a training process. SPH, as you know, it's very, very expensive. It's a particle method. And again, similar plots. It's interesting here to see at the interface, for those of you who are working on interfacing this type of different domains, having the Robin boundary conditions. If you just have R equals 0, which will give you a Neumann boundary condition, it doesn't work, or no, it works here. But depending on R, you can have divergence, but actually you can find a sweet spot. R is 1/4, gives you the fastest convergence. So parameterizing the interface conditions are Robin on both sides, as opposed to the standard Schwarz algorithm tells you to pass fluxes from the master to the slave, and then from the slave to the master displacement. But actually doing Robin is better, and then you optimize. So bottom line here is a finite element. If you put together a finite element and SPH, it will take 4 hours to solve this problem. A finite element deep on it will take 1 second. Of course, you spend time to train the deep on it, but you know, you have the neural operator around for other operations as well. So what I show you is the steady state. Why we started this was actually to do dynamical systems. How you do that in time, and I'm running out of time here. But just as this is a heat transfer problem. So, for example, we do deep on it here and a finite element here. But now we have diffusion, we're changing in time. And you can see what happens for one time step. Here we have to iterate. So basically, for diffusion, I write my neural network at the next iteration is, let's say, the previous iteration from the previous time step, which is steady state, plus this, let's say, just Euler integration, simple Euler integration. So you need to worry about this second derivative, and in fact, this second derivative will be computed here in finite element. Then we take the interface, then that goes into here, into the branch, into the trunk, sorry, and then here we put the neural network from the previous time step. So we can predict this second derivative now. So a neural network can predict whatever you assign to as labels. So here, for this particular case, I needed to have a second derivative because of the coupling scheme that I did in time. And then you repeat many times. All right, I'm out of time. Thank you for your attention. I just want to bring, if you're interested in this, we develop a course, free course, open source codes and everything. For NVIDIA, it's called Deep Learning for Scientists and Engineers. As I said, it's the only course that you find on the web that doesn't show cats and dogs. It's all about science. We concentrate on science, AI for science. This is our motto, and you can see here also the content. It's all free. You can just download for all educators. You can download the basics. We teach all the frameworks, TensorFlow, PyTorch, and JAX. We teach pins, neural operators. We teach DQ in neural networks. Also, we teach the modulus library that we built on the pins and deponents and FNOs. That 70% of what is the modulus library by NVIDIA is based on our work. And then we have many different projects that were given to us from people around the world, so one can carve out their own course depending if you're in mechanical engineering, if you're doing bioengineering, fluid mechanics, geophysics, and so on. So anyway, thank you very much. These are my sponsors, the Air Force. I lead a big consortium on multi-university research initiative with good people, and then also I am director of a Department of Energy new center is called Physics Information Intelligence, where we emphasize graph networks, neural operators, and spiking neural networks is something new that we're working on. Thank you very much for your attention. I'm sorry I'm not there to talk to you in person and socialize, but maybe next time. Thank you.
Thank you, George. Thank you for giving the inspiring plenary seminar. So we have time for questions. I'm just trying to test if the microphone will pick up the questions. So, any questions? Of course, if I ask, the microphone will definitely pick up my voice. I'm so close. Yeah. So, shall I make a start? Hi, George. You presented so many examples using both the multi-scale simulation framework and also the more recent PIN and the deep ONET framework. And many of these examples involve really phenomena that goes beyond the traditional standard tests. Things like if you're talking about linear elasticity, the parameters you require are easy to obtain. But for those complex problems, either it's medical problem or it's material problem, do you face a challenge of determining the parameters? And if so, how did you cope with them? For both cases, the data-driven model and the simulation model.
Right, so as you go down to smaller scales, let's say molecular dynamics, you have few parameters, right? Molecular dynamics, you have parameters for the potentials. In DPD, you also have similar parameters, but not as many as you want. So yes, your answer to your question, unless you go to quantum, you will not have any parameters. But as you go lower in scales, you have parameters. For example, a lot of work that they do in modeling biological systems using DPD is based on certain tests we do for red blood cells. For example, we stretch the red blood cells, we let them go through microchannels and so on. So, but from the relaxation time, we can find the membrane viscosity. From the stretching, we can find the modulus of elasticity. So we do static and dynamic experiments, which will close the system. So you do need some data even at this mesoscopic level. You're right. So you do need to have data. You always need to have data, but not as much data as you go smaller in scales. So that's the reason. As you go big in scales, you lump everything. Of course, you need to do lots of parameters. And as I point out, lumping is not always as we do in engineering. And the engineering approximation is too rough because we hide a lot of important details, like the memory, for example, that I talked about.
That's right. If you try, speak loud.
Thank you, Professor, for very nice talk. I would like to ask a question on this neural operator. How do you think it can handle high frequency inputs? Let's say if you have noise as an input, how do you handle these operators?
I think that, yeah. I think I heard what happens with neural operators if you have high frequency and also noise, right?
Yeah.
Actually, if you have noise inputs in general, just neural operator, you want to have noise inputs, perturbations, because these neural networks learn better from if you have noisy data. So that's one thing. But if you have huge noise and you look at uncertainties, there's ways to deal with that. In fact, the course I just described, we have a whole 3 hours dedicated to that. Now, in terms of high frequencies, all neural networks suffer from spectral bias. They choke in high frequencies, but there's a ways around that. You can put a multi-layer input frequency. So you can, for example, if you target hertz and kilohertz, you can have a feature layer, which is called feature layer in the input. So you can have signs of tens or hundreds of thousands of hertz. So you bias your neural network to capture that. This is not just for neural network. This is for any neural operators. This is for neural network. So you're right. When you have high frequencies, you suffer spectral bias. There's a way to do that. There's multiple papers now in the literature where they deal with the not just high frequency, but also high wave numbers will be the same thing. For example, so you need to have these extra feature layers. You have to design them very specific to the problem and the target range of wave numbers and frequencies that you're interested in. So, it's a solvable problem. Likewise, to do domain decomposition like methods that we have like X pin and C pin and so on. Combine pins with domain decomposition.
Any more questions from audience? Thanks, George.
I think I want back to ask questions in person.
Thanks, George. It's a lot of information from your talk. A lot to take away. I think many people or many audience, it's a very diverse audience here. Engineers, computer scientists, and we also have mathematicians as well. But perhaps because the breadth of the audience, we are still, without question, taking time to make lectures. Yes, please.
I think there was a question back there. I can see.
That's right. Yes.
So I, in the area of machine translation, there were very many approaches, many ideas to integrate analytic knowledge like syntax knowledge with data-driven approaches, and it has all failed. It all turned out that taking only data-driven approaches outperform always attempts to integrate analytical knowledge and data-driven approaches. So I'm wondering, do you see a parallel there? This is a kind of a similarity, what you're trying to say, and how is your take on that?
I'm sorry, can you please repeat? I didn't.
Okay.
This one was beyond the range. I think. I didn't.
All right. Let me repeat the question. So the question is in the AI, the development of the AI, the history of AI development. There have been multiple routes where people trying to integrate like knowledge graph or synthetic logic-based framework with to deliver AI. But these days, it seems that the pure data-driven AI outperform all those traditional approaches, and even the attempt of combining them does not seem to show promising evidence. So those pure data-driven seem to just by adding more data, brute force, just does the job. So how do you see from this approach, PIN, for example, or deep or net, which obviously connect physics and data-driven together? Is this something you have thought about, or how you will build on that?
Yeah, so I can talk about pins for example. The idea was to integrate data into our simulations, because if you have a finite element method, even if you have one point, you don't know what to do with it. you have to set up a data simulation method, so that would be so expensive that you run. So in our case, the more data we have, the better for various reasons. One is you bring the reality from data. The other one is actually technical reason. As you know, we solve a complex optimization problem, non-convex optimization data in thousands or millions of dimensions. So when you have data, it helps us a lot because you anchor the solution. Every data point you have, you eliminate the multitude of solutions. So you go towards the global minimum, which is the answer that we want. And so the data helps a lot. But at the same time, with pins, what we wanted to have conservation properties, right? You can have data. Take a case where the data is not very accurate, and you're doing kinetics. For kinetics, you need mass conservation, otherwise some species will disappear. So in the pins, we guarantee that we'll have both. We don't need a lot of data, but we need. That's why in my schematic I have a half bucket. Half bucket was blue, half bucket was gray. So we can work with gray boxes. When you have all data is all black boxes. Yes, if you have the perfect data, the perfect measurement with zero error, a data-driven approach will be okay. Now, commercial machine learning is different, right? Because they try to recommend shoes or not. But here we try to capture instabilities, bifurcations, and so on, which are very, very difficult with this method. So you have to get accuracy, really good accuracy. still I believe that the accuracy we have with pins or any neural network method is not good enough. For example, we cannot resolve turbulence using neural networks. Okay? If we have lots of data, then we can do something. But it goes back to this spectral bias. So we are not, pins is not perfect, but it provides some sort of good compromise between what the data, where the data drives you, and also what respecting the physics. As I said, mass conservation is very important. Energy conservation is very important. Also, doing long time integration of this is very important. So, just from data, I don't believe that you can do. I missed the first part of the question, so I'm not exactly sure what you have in mind unless you give me an example. But as I said, pins is sort of try to compromise between what we used to do as just simulation from physics, which is I call sterilized case, versus a realistic case where there's uncertainties, there's noise, pins can bring all that reality into the simulation in a seamless way. Maybe I didn't answer your question, but in person, I probably could do better.
Yeah. Would you like to continue to drill deeper?
Yes, I can give an example. For instance, in ChatGPT, people have tried to integrate in similar frameworks also syntactic knowledge.
Yeah.
But that doesn't work. So that doesn't increase the performance of those systems. In machine translation systems, you can try to have a data-driven approach based only on parallel data, and you can try to add to this syntactic knowledge or something like that.
I understand.
It doesn't add.
No. That's I said. Here, so let's take the neural operator. So you use data and let's say physics you can also have physics to train neural operator. But if you endow the neural operator with properties like symmetry or the Lie group properties and so on, then actually Galilean invariance. If you do that, if you constrain with all this, then you learn much better with much fewer data, and then the prediction is much more accurate. So some sort of syntax into the neural operator during training helps actually a lot here. So myself and other people, my group and other people have shown that, and in fact, currently I'm reviewing a paper, I'm handling a paper in one of the journals that tries to train neural operators using only properties of the operators, without labels, without data. So I think in our case, where it's very math is different than language. It pays off big time if you bring in all the properties of the operator, just like equivariances that you have. And I have demonstrated that, for example, in mechanics problems. We have a paper that we're trying to find metamaterials. Design metamaterials. If you bring in Galilean invariance and some properties, all sorts of these other properties, it turns out that you get superior accuracy with fewer samples for training. So I think a syntactic approach would be very appropriate here.
So first of all, thank you very much. It was a very inspiring presentation, very comprehensive, so we really enjoyed it. So I would like to have your opinion. So in engineering, there are a couple of problems that are extremely challenging. You've mentioned already turbulence. Fracture is another class of problems which are extremely challenging. And I would like to know if you use these techniques with neural operators, do you think that we will have a chance to find hidden relations there and discover the physics with these approaches that we haven't yet managed to succeed so far?
Right, you're right. Most of the demonstrations that we have done so far is kind of rediscovering the equations that we know and so on. So you can see the promise of neural operators actually to find, it's a system identification in some sense, right? So the question that you answer is very timely because I'm working on a couple of proposals from DARPA, which after a long time they went back to turbulence and they tried to do funding for turbulence, which they haven't done for decades here in the United States. And they pose a problem like that, like exactly what kind of correlation, what kind of measurements you need so that you can break the deadlock in turbulence going to high range numbers. And I believe, and here's my proposal I put there in the open, that doing the Navier-Stokes plus adding a neural network that you try to identify the neural network as a correction term. If you have enough data, let's say correlations, point correlations or PIV data that you embed in the turbulence equations, I believe you can find closures. I believe you can find closures which go beyond the eddy viscosity models, because as you know, the stress and the strain rate are never aligned. So all these eddy viscosity models in LES are all wrong in complex flows. So I believe you can discover this type of correlations, not just because we have neural operators, because we can measure now things that we couldn't measure before, even in temperature with the infrared camera. You can, that's a lot of points working with infrared cameras or portable. They call it, DARPA wants to do these tabletop experiments, simple experiments that will give you correlations and then on the small scales, and then see if there's universality in these correction models. But I made a comment earlier about LES and how people went to what is computable at the time. It was Magorinsky introduced, and we never went past that point in some sense. But if you look at early attempts of mass science, I was a postdoc there. There was a guy who introduced the self-similarity model, which is the right model, for example, breaks away from the Prandtl model. But they couldn't make it stable because it introduced negative diffusion. But we know now how to handle that using regularization techniques and so on. So I guess the answer to your question is, I believe both in problems like fracture and turbulence, integrating the right data could break the deadlock. We haven't done it yet, but the promise I think is there. So but it's not just the neural operators. I think it's also the diagnostic tools that we have working synergistically there too. I think it's just like how the GPUs came around, and then we had the theory for neural networks. So the field took off. It's something like that the measurements are there, good measurements are there, the tools, and also this approach of integrating data into simulation seamlessly is there.
Thank you.
Okay, two more questions at the panel. Is that okay? Yeah.
It's fine.
Thank you for the presentation. And, my question is, I think it's a bit about physics. So when I try to implement lens for solving PDE, the problem I run into most of the time is when using atom optimizer, the reduction in loss is quite unstable. There are a lot of fluctuations like when I use an atom optimizer, which can be stabilized sometimes when I use LDFTS, but it's not completely reliable. So is the depot net method more reliable? Is it more stable? Does it have a more stable reduction of loss when you use an optimizer? How does it work?
Well, it's hard to tell. It depends on the data, but certainly for deep ponent you need more data, right? Because you have a plurality of conditions, let's say, not just one boundary condition and so on. So you're going to have let's say if you look at kinetics, stiff kinetics, you're going to have include stiff kinetics, but also you're going to include other kinetics. So it could be probably better, but there are ways to deal with convergence issues. For example, you can use regularization. It turns out we had a similar problem with Navier-Stokes equations recently. So what we did is we added actually a smoothing term, like an artificial viscosity term, into the loss function. So we end up having a LES type formulation to get the DNS solutions. Because the reason for that is, as you know, you try to minimize a landscape, the loss landscape, which has, for multiscale problems, which is the topic of this conference, becomes very corrugated. So if you visualize the landscape of, so there are several ways. You can use a ResNet deals with ripples in the landscape, but also you can add a little bit of smoothing, like as I said in Navier-Stokes, I use like a eddy viscosity. The eddy viscosity is not good, but I just added very little, another regularization method to smooth. If you smooth then you avoid the saddle points, which are the bad minima, and that's why you get stuck. So
So trying to see how your landscape looks, and then you do the appropriate thing. There's also another new optimizer by. It's a method that was developed automatically by genetic programming by Google. It's called Lion. Instead of Adam, you can use Lion, Lion. So that seems to have less variance and actually much faster conversion. It's a paper that Google did, I think, last year, and then the code is available by Google.
Yes.
Thank you for the inspiring talk. When you mentioned that in physical problems there are different layers where often different physical rules apply, and there are boundaries between those. And sometimes in practical applications, one may not be aware exactly which physics apply or when each of those physics apply. Have you tried to incorporate some stochastic variables or stochastic functions to determine which physical laws apply to the data when you're changing?
That's a very good question. I think in terms of something new, is there something new here with neural networks? I think that there is something new, and that's actually the area where we can make improvements. And the reason I say that is because I believe that the gray box model will be a case where, and I mentioned briefly, is let's say reactive transport. I don't know the reactions, right? So you're saying you don't know the region where this could happen. The same thing. But in that case, you assign a correction term or a discrepancy term, if you like, which would be represented by a neural network, so a pins or a DeepNet, and then you can actually, from data, find that. So the data will find that term and what's happening in that region. So I think that is a great area of research, innovative research. We have presented a paper recently, we call it model uncertainty, where, because you can ask me the same thing, basically you ask me, what happens if you misspecify the physical model in pins, right? It's the same thing. So what we did, you can look at that, I think it's a JCP paper, Journal of Computational Physics, by name and model uncertainty, and you will see that we actually take a case where you have a non-Newtonian fluid, but you dial in equations for Newtonian fluid. If you add a neural network and you have enough data, you can actually find the correction, the stress-strain relationship. So you can discover the neural network. You discover first the neural network, then you can use a symbolic regressor, a modern symbolic regressor like PYR or any of symbolic regressors, and you can find explicitly the correction. So we have an example like that where we pretend we don't know that it's a non-Newtonian fluid. We dial in the wrong equations, but we allow a discrepancy model, and that's the gray box. I call the gray box because that's a missing physics. So the missing physics will be captured by the neural network, and of course, you need to have enough data to be able to determine that neural network. So, but I believe for me, that's a great area of research where you can actually make good progress, new progress, innovative research, what you just described.
Thank you, Ron. Do we have more questions? Final one. So, all right. Thank you again, George. A very inspiring talk. A lot to take away from here. And I wish everything well for you. And it's pity that we can't see you in person here in Porto. Yeah.
Okay, great. Thank you very much.
Thank you.
Take care.